Right, I'm going to go over a triple higher paper 2. It's the questions from SP10 unit, which is electricity and circuits. So these questions will be very general about electricity and circuits from any exam board. All these questions have been taken from recent exam papers from the last 3 years, and you can see there's 57 marks worth of questions. So the examiners like to ask you questions about electricity and circuits. Question 1. Explain with the aid of a circuit diagram the method a student could use to investigate how the resistance of a single lamp changes with the potential difference across the lamp. Okay, if we're going to get the resistance of the lamp, we need to calculate voltage and current. Voltage is measured with a voltmeter and current is measured with an ammeter, so we need to incorporate those into the circuit. And they're asking about how the resistance changes, so we need some kind of way of changing the voltage and current. So the first thing we need to do is measure the voltage and measure the current and work out the resistance. Then once we've done that once, we will change the size of the variable resistor, which will give us another voltage and current reading to compare. So you want to compare the original voltage and resistance of the bulb to the new resistance and determine the relationship. For example, if at first you make the variable resistor small, that means that the voltage on the bulb will be big. And you'll find out what the resistance will be. Then what you do is make the variable resistor big, and that'll make the voltage on the bulb be small. And then you see what the resistance is. Compare this first resistance of the bulb with the second resistance, and you'll be able to see, as the voltage got smaller, what happened to the resistance. Question 2. Figure 19 shows 2 electrical devices for heating water. Right, you've got an immersion heater that's being run off a battery, and you've got a heating element of a kettle ran from the mains. The current in the element of the immersion heater is 14 amps. The power of the immersion heater is 130 watts. Calculate the resistance of the immersion heater. Give your answer to 2 significant figures. I always like to underline things that are important. So we know the current, we know the power, we need to calculate the resistance. Is there an equation that links those 3 things that you're supposed to know? Yes, there is. Power equals I squared R. Now we need to rearrange that. So therefore, R equals P over I squared. Pop the numbers in. Now they wanted the 2 significant figures, so that's 0.66. The current of the heating element of the kettle is 8.3 amps. State 2 differences between the movement of charge in the heating element of the kettle and the movement of charge in the immersion heater. Well, the charge that will be moving will be electrons. And as you can see, the heater is powered by a battery, which is DC, which means that the electrons travel in one direction. The kettle's powered by the mains, which is AC, and the electrons in AC go backward and forward. And the other thing, charge equals current times by time. The current is 14 amps in the immersion heater, whereas in the kettle it's only 8.3 amps. So if we just rearrange that equation, current is the rate of flow of charge. So if you've got a bigger current, it means you've got more charge flowing per second in the immersion heater. Question 3. A student investigates how the current in a lamp changes with the potential difference across the lamp. The student uses the results to calculate the resistance of the lamp. The results are shown in the table in figure 5. One value of resistance is missing from the table in figure 5. Calculate the value of resistance that's missing from the table. Right, well, voltage equals current times by resistance. Therefore, resistance is voltage over current. The voltage is 5 and the current's 0.26. So that equals 19.23. You can see there's no decimal places in the values of resistance they've gave you. So we'll just round ours down then to 19. Make sure you show the full value up there just in case. The student writes this conclusion. The resistance of the lamp is directly proportional to the potential difference. Comment on the student's conclusion. Use information from figure 5 in your answer. If you don't use information, you're not going to get the full 3 marks. The other thing to pick up on there is the use of the word directly proportional. Now, directly proportional basically means as one thing goes up, the other thing goes up as well, by equal amounts. So if one doubles, the other doubles, or if one thing trebles, the other thing trebles. Right, let's have a look then. If we have a look at the voltage of 2 and we double it to 4, does the resistance double from 14? Does it go to 28? No, it doesn't. It's miles away. So what we can say is that as the voltage gets bigger, the resistance gets bigger, but as the voltage doubles, the resistance does not double. Watch, we could take some more values. If we double it from 3 to 6, does the resistance double? 17 would go to 34. No, it doesn't. A lot of students forget to quote the information for that 3rd mark. And also a lot of students don't realise what directly proportional means. Part 3. The student used a power supply that had fixed output voltage settings. Each of these outputs has a whole number of volts. So that just means like 1, 2, 3. Describe how the student could add a component to the circuit that would provide a continuously variable voltage across the lamp. Well, you basically want to add a variable resistor in series with the lamp. So for example, because it's in series, remember the voltage in a series circuit gets shared. So you could adjust the variable resistor however you liked it, and that would control how much voltage was going on the bulb. And you could have any size voltage you wanted. Question 4. Part A. The technician investigates a light-dependent resistor, LDR, connected in series with a 120 ohms resistor and a voltage source. The technician measures the voltage across the LDR and also the current in the LDR. Which one of these circuits should the technician use? Right. Well, the main thing to notice straight away is that the voltmeter should be in parallel across the LDR and the ammeter should be in series with it. So A is clearly wrong. B has got the voltmeter in the right place and the ammeter in the right place. So it looks like B is correct. We'll just check the other ones. Well, this is wrong because the voltmeter is in series, it should be in parallel. And this one's also wrong because the voltage once again is in series and it should be parallel. So the answer is definitely B. Part 2. When the LDR is in bright sunlight, its resistance is 185 ohms. The voltage across the LDR is then 7.2 volts. Show that the current in the LDR is about 0.039 amps. So once again, what do we know? We know the resistance R is 185. We have got voltage V, 7.2, and it's asking us to work out the current to show that it's about 0.039. Do we know an equation that links VI and R? Yeah, of course we do. It's Ohm's law. V equals I times by R. Therefore, let's rearrange it and pop the values in, and it should come out somewhere close to 0.039. And it does. So they said it should be 0.039, thereabouts, and we have got 0.0389, which would round up to 0.039. Part 3. Complete the sentence by putting a cross in the box next to your answer. The current in the 120 ohm resistor is much more than the current in the LDR, much less than the current in the LDR, the same as the current in the LDR, or the opposite of the current in the LDR. Don't even know what that means. Right, let's have a little look. Well, it's a series circuit, and we know that the current in a series circuit is the same everywhere, so it's going to be the same. The current in the 120 ohm resistor will be the same as the current in the LDR, which is C. Part 4. The technician repeats the readings with the LDR in different light conditions. The table gives two of the readings. So when it's bright, the current is 0.039, and when it's cloudy, which means it's getting darker, you can see the current is less. Explain why the two current readings are different. Well, we know that current is controlled by the size of resistance. So since this current got smaller, it must mean that the resistance of the LDR when it got darker increased. And if it was worth 3 marks, we'd get 3 marks for that. Question B. The photograph shows a temporary traffic sign. The traffic sign uses many small lights, all powered by a rechargeable battery. These lights need to be very bright during the day so they can be seen clearly. They do not need to be as bright at night. Explain how using a light-dependent resistor can make the energy stored in the battery last longer. Okay, let's compare the LDR during the day and what's happening at night. During the day, the LDR resistance is low, which means that the current in the circuit is high, which means that the battery is using lots of energy, which means that the bulbs are very powerful. Power equals energy transferred over time. So if you're using lots of energy per second, it's going to be very powerful. It's always good to back up your answers with a calculation if possible. If the bulbs have got lots of power, it means they're very bright. And that's what it needed to be during the day. Now let's compare that to at night time. At night time, the LDR's resistance is high, which means that the current will be low, which means there's not much energy being used. If you wanted to back that up with an equation, use this. Emmerdale is on ITV, which is energy is current times by time times by voltage. So if the current is less, then the energy will be less. Now the bulbs won't be very powerful, but that's absolutely fine. They don't need to be as bright at night. Now although we won't get a mark for saying that because it's already said here, we can now go on to say that the battery is using less energy at night, so the battery will last for longer. Now I've marked lots of exams over the last 22 years, and I'm quite happy if a student gives me an answer structured like that, with the use of a table. I quite like it when the students put their answers down as bullet points, because it shows me that they're expecting a mark for each one of these. Not all the time, remember, with regards to that statement, but most of the time. And besides, even though it's worth a 6-mark question, they've got a lot more than 6 marks there, so they'll easily get the 6 marks. Question 5. A man monitors how much money he spends on electricity. He uses a device which calculates the cost of electrical energy used. He connects his 2.9 kilowatt electric kettle, so that's power, to the 230 volts main supply, so that's voltage. Calculate the current in the kettle. So we've got power, we've got voltage, and we're looking for the current. Is there an equation that relates power, voltage and current? Yes, there is. PIV. Power equals current times by voltage. Let's rearrange that. Put the numbers in. Now remember, 2.9 kilowatts is 2,900 watts. 1 kilowatt equals 1,000 watts. And that equals 12.6 amps. Question 6. A resistor is connected to a power supply. The potential difference across the resistor is 6 volts. So we know voltage. Which of these corresponds to a potential difference of 6 volts? Okay. So it wants us to find some alternative units for voltage. Now the way you do this is you write down the equations you know for voltage. So we know that voltage equals current times by resistance. So 1 volt would be the same as 1 amp ohm. Is amp ohms here? Joules per ohm, amps per coulomb, joules per coulomb, amps per coulomb. Well, that's not quite the same as amps coulomb, because amps per coulomb would be current divided by resistance, and that does not equal voltage. To get voltage, you need to do current times by resistance. So, do we know another equation for voltage? Yep, we've got EastEnders equals the Queen Vic. Energy equals charge times by voltage. So let's rearrange that to get voltage. So therefore, voltage equals energy over charge. So 1 volt is the same as 1 joule, because energy is measured in joules, per coulomb, because charge is measured in coulombs. So 6 volts would be the same as 6 joules per coulomb. Is that an option to choose from? Yes, it is. The answer's C. Now remember, if it's a question worth 1 mark, you should just be spending 1 minute on it. So you need to go through this process in 1 minute, if possible. So you've got to make sure that you're learning all the different equations. I've got a nice little video with all the equations on, and at the end of the video, you take a screenshot and you've got all the little equations you need, so you can revise from those. I'll put a link at the top of the screen. The resistor remains connected for a period of time. The current in the resistor is 200 milliamps. Right, well, let's convert 200 milliamps into amps. And you do that by dividing by 1000. So we know that the current, I, is 0.2 amps. The total charge of 42 coulombs flows through the resistor, so we know that Q, the charge, is 42. Calculate in minutes the time, so we're looking for time, taken for this amount of charge to flow through the resistor. Is there an equation connecting Q, I and T? Yes, there is. Quit. Q equals I times by T. So therefore, let's rearrange that. T equals Q divided by I. Put the numbers in. And that equals 210 seconds. Now they want it in minutes. So if we take 210 seconds and we'll divide that by 60 seconds per minute, that'll tell us how many minutes there are. So that's 3.5. Part 3. Calculate the total energy transferred by the 6 volt power supply when a charge of 42 coulombs flows through the resistor. So we're looking for the energy. Is there an equation that links energy, voltage and charge? Yes, there is. EastEnders equals the Queen Vic. In England, there's a programme called EastEnders and the main pub is called the Queen Vic. So that's how I remember that equation. Watch my video to do with energy if you want to learn more. So that equals 252 joules. Question 7. Figure 20 shows the 3-pin plug used to connect the kettle to the mains. The fault occurs in the kettle, causing the live wire to touch the metal case of the kettle. Explain how the safety features of the plug operate when this fault occurs. I've got a lovely video all to do with the earth wire that'll show you how to answer this. There's a link at the top of the screen now. Now the answer's always the same, so for 6 marks this is how to answer it. If the live wire becomes loose and touches the metal casing of the kettle, this will cause a short circuit inside the kettle. So what that means is that there'll be much less resistance inside the kettle. Because there's less resistance, the current will increase. Because instead of the current going around a high resistance filament inside the kettle, the current will simply pass through the earth wire, which has got very low resistance. Now because there's so little resistance in the circuit, that'll cause a high current. Now remember, before the current goes through the live wire, it's got to go through the fuse. If suddenly there's a big current coming in, that'll blow the fuse. Because the fuse, remember, is a thin wire with a low melting point. And if you've got a large current, that causes the wire to get hot, which melts the fused wire and breaks the circuit. If you haven't got a clue what I've just said, seriously, watch my video about the earth wire and double insulation. It'll also explain to you why you don't need an earth wire if the kettle is not metal. A lot of kettles have got plastic casings. That's a common question. You can't afford to get it wrong, so make sure you check that video out. Question 8. A resistor is connected to a power supply. The resistor becomes warm while there is a current in it. Explain why the resistor becomes warm. Well, the heat is always caused by current, and current is a flow of electrons. And as the electrons bump into the positive metal ions, it causes friction, and the friction causes heat. Heat is basically vibrating particles. So kinetic energy from the electrons are transferred to the positive ions. Question 9. Which of these symbols is used to represent a thermistor in an electrical circuit? Well, that's a diode, D, I, O. That's a light-dependent resistor. That's a motor. And that's a thermistor. So the answer is D. I've got a lovely video all to do with circuit symbols. Click the link at the top of the screen now. Question 10. Figure 18 shows identical filament lamps connected together in a 12-volt power supply. Calculate the potential difference across each lamp. So calculate the voltage. Right, well, you'll notice that these lamps are connected in series. And what we know is that voltage gets shared. So we've got 12 volts divided by 1, 2, 3, 4, 5, 6, 7, 8 bulbs. So each bulb gets 1.5 volts each. Part 2. The power output of each lamp is 0.75 watts, so we know the power. Calculate the resistance of each lamp. And it's worth 4 marks. Okay, to get the resistance of something, if we start with Ohm's law, V equals I times by R. We'll rearrange that. So R equals V over I. Since we're wanting to know the resistance of each lamp, we just use the voltage of each lamp, not the total voltage. 12, no, just 1.5 volts. Now the thing is we don't know what the current is. Right, so what do we know? We know the power, and we know the voltage is 1.5. Is there an equation that connects power, voltage and current? Yes, there is. PIV. So if we rearrange that to get current, we'll be able to solve what the resistance is. So that's half an amp. So let's pop that over here. So that's 1.5 over a half, which is 3 ohms. And that's why they're giving you 4 marks instead of just 3 for the calculation, because it's got 2 steps to it. And finally, question 11. Figure 16 shows a cardboard tube with a wire coming out from each end. There are 2 10 ohm resistors inside the cardboard tube. The potential difference of 6 volts, so that's our voltage, is connected between P and Q. There is a current of 1.2 amps in the wires. That's our current. Deduce how which means find out, Deduce how the resistors have been arranged inside the cardboard tube. Right, well, they've either been arranged in series or they've been arranged in parallel. So first of all, let's work out what the resistance is, and then we'll be able to tell whether they've been connected in series or parallel. So Ohm's law, and then rearrange that to find resistance. Okay, since we've got 6 volts, the resistance is creating 1.2 amps, the resistance must be 5 ohms. Now, if we had a 10 ohm resistor and a 10 ohm resistor connected in series, that would give us 20 ohms. Well, we've only got 5 ohms, so they must not be connected in series. Now, back in the olden days, you did have to know the equation for calculating the resistance when 2 resistors were in parallel. The equation now is just used at A level. All you need to know at GCSE level is that when you add resistors together in parallel, their resistance will be smaller than what the resistors were. So the resistors were 10 ohms each, so the resistance is going to be smaller than that. And in fact, if you've got 10 ohms and 10 ohms, it will actually be 5 ohms. I can't resist myself. I've taught A-level physics for 20 odd years. I'll quickly show you. So 1 over the total resistance equals 1 over 10 ohms plus 1 over 10 ohms. So 1 over the total resistance will be, well, a tenth plus a tenth is 2 tenths. Now 2 over 10 is not the answer. 2 over 10 is 1 over the answer. So if we flip this left hand side and we flip the right hand side, we'll have RT over 1, which is just RT, is going to equal 10 over 2. And 10 over 2 is 5 ohms. So there we go. You don't need to do any of that. But I do like it if you understand where things are coming from. So the resistors must be connected in parallel because the 2 resistors together are less than any one of the single resistors. That's how we see it at GCSE. Okay, well, I hope that's been really helpful for you. Good luck with any exams you're sitting this summer or beyond. Please subscribe to my channel. There'll be lots more videos like this to come, trying to help you to pass your exams. Nothing further to say except for work hard, be nice, and bye for now.